Hi, my name is Oluwaseun Martins. In this video, we'll be looking at another example of your perceptron learning. In this case, we'll be looking at this sonar sensor data. This is a CSV file with the input of a sonar sensor reading, of several variables in these columns, and we have the label column here, whereby it is specifying if it's a rock or a mine in this case. So RM, rock instance, and mine instance. So this is sonar sensor reading for ships, whereby they use it to determine if a certain object in the ocean is a rock or a mine, because mine are like underwater explosives that are used to destroy ships. So ships always have these sonar sensors on them to help use echolocation to determine if a certain obstacle is a rock or a mine. So what we just want to do here was use a perceptron to build a model that can determine whether a certain signal from the sonar is a rock or a mine. So because from this label column we can see there are two classes, so which means we can use a perceptron in this case, because we know that a perceptron is a binary classifier. We can use a perceptron to do this work. And also we must note that based on the nature of the label, we can see that this is a classification problem. It is not a regression problem, because there are two classes of R or M, so it's a classification problem. And in that case, we can use a perceptron learning to do this. So let me just switch to my Python, guys. This is my Python, guys. And the first thing I want to do here is to bring in my libraries that I'll be using. So import matplotlib lib.plt.pyplot as PLT. Import my TensorFlow. I already explained what these lines are for in my earlier video on the AND logic gate. So import TensorFlow as TF. Import TensorFlow.compat v1 as TF. Disable v2 behaviors warnings. So import NumPy as MP. Pandas as PD. sklearn.preprocessing. Import label encoder, because I'll be doing the one-hot encoding, so I need the label encoder for my one-hot encoding. Also from sklearn.utilities, import shuffle. Why I need to do this shuffle is because when I went through the data, I can see that I have instances or observations of R in sequence, and also M in sequence. And because I'll be splitting this data into training and testing of 80 and 20%, I want my model to be built on the training of observations that has to do with rock instances and mine instances. So I need to shuffle this data so that I won't be training just with rock instances or mine instances alone. I want to train my algorithm with both instances, so I need to shuffle this data. So from sklearn.models again, _selection, import train _test _split. So I can split that data into training and testing. So let me just run this, and I have all my libraries in. So this is why I'm doing the one-hot encoding, guys. I've told you what one-hot encoding is, but let me just go back to the one-hot encoding explanation just to refresh your memory. So for the one-hot encoding, when you are dealing with let me increase this a bit. We are dealing with classification problem in neural network. You need the one-hot encoding, because in your classification problem with neural network, you'll be doing the cross entropy and softmax eventually. So you need one-hot encoding to do that calculation. So what the one-hot encoding does is to create individual colons, from the uniqueness in the entry of your label. So in this case, I have two features, x1, x2, and the label here is y, having class 1, class 2, class 3, class 1, class 2, class 3, class 3. So the one-hot encoding will create individual colons from the unique entries in your outputs or your label colon. So in this case, the uniqueness here is class 1, class 2, class 3. So class 1, class 2, class 3 as individual colons. Now this observation here result into class 1. So class 1 will have 1. Class 2 and 3 here will have 0. This observation here result to class 2. So class 2 here will have 1. This one will have 0 and 0. This one result to class 3. Class 3 will have 1. This and this will have 0. This one is class 2. So class 2 will have 1, 0, 0 for these instances. So this is the one-hot encoding equivalent of this output. So in the case of the one we are talking about, we have just two uniqueness, R and M. So one column for R, one column for M, and it will have 0 and 1, 0 and 1 wherever it's applicable. So let me just explain the cross entropy alongside this. So let's assume this is the model output. You understand? Just assume that these are the model outputs. Now, for us to do a cross entropy, we must first of all do the softmax activation function. Let me go back to the activation function in this case. The softmax is having this mathematical model. So this is the sigmoid function. This is the tanh, this is the ReLU. So this is the softmax in this case. So the model of softmax is exponential zj divided by summation of k equals 1 exponential zk. So what that means is, for the softmax, you use a softmax layer when you have output more than 2 classes. You understand? So it gives you the probability of the class that is probably the outcome in this case. So exponential zj divided by summation of exponential zk. So if you go back to the Excel, so for me to do the softmax in this case, I need to, because I have more than 2 classes in this very example, so I need to do the exponential of the zk, which is the exponential of the output. This is the exponential of this exponential of this exponential of this. So that is what you have there, row by row. All the exponential of these outputs are what you have here. So for the softmax, it is exponential of this instance divided by the summation of the exponential of all of this instance. So that's what you have here. So that is L5, which is L5 divided by the summation of what? L5 to N5. So this is what the model here is saying. Exponential zj divided by summation what? Exponential zk. So that's what is happening here. So this instance equals this exponential divided by all of this. This instance equals this exponential divided by the sum of this. This instance equals this exponential divided by the sum of all of this, gives you this. And that is how all of these are generated. In this case, that's what the softmax. Now, if you look at the softmax, the softmax is saying class 2 is having the highest probability for this observation. However, if we go back to the output, it's class 1, not class 2. So we need to do a cross entropy on this softmax to know which class is actually correct. So that's why we are doing the cross entropy here. And the model of your cross entropy here is minus sum into your one-hot encoding output which is in this case f5, times the log of the softmax of that instance. So this one equals minus sum the one-hot encoding instance of that same output, which is f5 in this case, times the log of the softmax instance. So that is how we, so this one will be the minus sum one-hot encoding output of that instance, which will be 0, times the log of the softmax instance, So that is how we got the cross entropy. So from cross entropy now we can see that cross entropy is saying no, the class is actually 1 because that is having the highest value. This one is saying the class is 2 and it's correct. The class here is 2. Class here is 3 is correct. Class here is 3. Class here is 1 is correct. Class here is 1. Class here is 2 is correct. Class here is 2. Class here is 3. Class here is 3. Class here is 3, and class here you call it 3. So that is this explanation once again. So going back to the Python file. So I want to do the same one encoding using Python. So I'm creating a function definition, def one_hot_encode. What am I encoding? I'm encoding the labels. That's the argument I'm taking in. So n_labels equals length of what? The labels. What is the length of the labels? I want to know the number of observations that I have in this file, because when I'm creating the one-hot encode equivalent of these labels, it must have the same length as the observation of this very data. So the length of the labels. So n_unique_labels equals length into np.unique labels. So what I'm doing here is that I want to know the unique entry in the label colon, the length of it, the length of the unique entry in the label colon. I want to know. That's what I'm doing here. So one_auth_encode equals np.zeros, and the shape of that very matrix is this n_labels, which is this n_labels, which is this line. Whatever the value here is the number of row, and that is the length of the labels. And the uniqueness, which is this, will be the number of colon. So that will just create r:(m:) having zeros all through in the length of this number of observations. That is what this line of np.zeros will have done. But I want to do a one-hot encode really, whereby the instances of m will be 1, just like I explained here, and the instances of r will equally be 1. So to do that, I'm now saying one_auth_encode np.arrange into n_labels, labels equals 1. So when the labels itself, is now r or 1, when the observation is that r or 1, replace it in the one-hot encode equivalent with 1. Whenever the instance is r or m in the original data, then replace it with 1 in the one-hot encode equivalent, and I'm returning the one-hot encode. So that is what this line is doing, just to create one-hot encoding. So this is my Sonar data. I want to actually bring in that CSV file. So I'm saying df, that's identifier, df equals pd.read_CSV. So read this CSV file that has that. This is the file path to that very CSV file of Sonar that I showed you. So print, I want to know the number of colons that is there. Print this string length df.colons. Why I'm doing this is because for me to know the number of colons that are there, because ideally these two lines I didn't put it initially. Let me comment it out. Let me comment it out so that You understand what I'm saying? Let me comment out these two lines and run this line. So it's from this print line I know that, okay, I have 61 colon. So that means 0 to 60 in the case of Python, because Python starts its own index from 0. So 61 colon will mean 0 to 60. So that means my 60th colon now is actually this very colon. You know, that's what it means. It's actually this colon, and that is my label colon, which is my y. So that's why I now said, okay, let my x be what? 0 to 60 dot values, and let my y be the 60th colon. So x equals df into df dot colons, and the range is from 0 to 60. That will take it from 0 to 59 actually dot value. So the values there alone, that's what I'm picking. And my y is df into df dot colons and the 60th colon in this case, because this one are string, so I don't need to put dot values in this case. So that will now assign those number of colons as my features for my x, and the y will now take the label colon. So here now is where I'm doing the label encoder. This is what actually makes the one-hot encoder work. So encoder equals label encoder. You will recall that we brought in that library already, label encoder, from the sklearn.preprocessing. So encoder.fit y, I'm fitting the label encoder to y. That's what makes the 1 and 0 possible on the y. So encoder.fit it to y. This encoder has been called as the instance of this label encoder. So I'm fitting this label encoder, so to say, to my y, which is the 60th colon. That is the label colon. So my y now equals encoder.transform. I'm transforming my y into the one-hot encode version. And the capital Y now is the one-hot encode version of y. So y equals 1 underscore hot underscore encode into y. So this capital Y is the one-hot encode version of the y, which I use label encoder to transform into the one-hot encode. So what has happened is that in this case, this now becomes my y, capital Y, which this is now the small letter y. This is the one-hot encode version is the capital letter Y, and small letter y is the actual y. And that's what has happened here. So I can just run that line. So the next thing I want to do is to do my train test split and shuffle. So before I do my train test split, I need to shuffle first. And I'm doing the capital X, capital Y equals shuffle into X, comma Y, comma random underscore state equals 1. Why I'm doing this random underscore state equals 1 is such that whatever way this data is shuffled, anytime I run the code, that's the same way it's going to be shuffled anytime I run the code. If I don't put it there, anytime I run the code, it's going to give me different shuffle, and I don't want that. So I want to have the same shuffle anytime I run the code. So that's why I'm saying X, comma Y, shuffle, capital X, capital Y, the one-hot encode version. This is the capital Y, X, comma Y, random underscore state equals 1. And this is how I'm doing the split in train underscore X, comma test underscore X, and comma train underscore Y, comma test underscore Y equals train underscore test underscore split. Capital X, capital Y, my test underscore size is 0.2. That's what's it called? That's 20% to be my testing data. And random underscore state equals 42, just to ensure that anytime I run this code, the same observation that will serve as my test of the 20% will be the same one that will be serving as my test of 20% anytime I run this code. So I run that line again. So here I'm defining my hyperparameter for my perceptron, which is my learning rate and my epochs. So learning underscore rate 0.1, training underscore epochs, in this case 1000. So here I'm just creating an array to store my cost history. So I'm creating an empty array. So cost underscore history equals mp.empty into what is the shape? just one colon. Shape equals, in this square parenthesis, 1 means colon. If it's 0, means row. So in this case, it's 1. So that's 1 colon for this cost history, just to print my cost, comma, D type equals float. The data type will obviously be float for my cost, because my cost will come from my loss, which is the mean squared error. It will be a float. So that's why the D type equals float. So here I'm trying to view the dimension of my features, because I know my weight will multiply my feature X in a matrix multiplication, and I know that my feature X is having how many colons? Is having a certain number of colons. I can actually go back to say, okay, it is 59, but I can just use the shape into a parenthesis of 1, so that I don't need to do that calculation. Python will do that. So I'm saying my n_dim, the dimension of my feature or features X, my n_dim equals the number of colon of it. So capital X dot shape into 1, this line. Okay, let me just say print n_dim. If I print this line, I will see the number of colon that my X is actually. And n_class, I have just 2 classes, which is R and M. So we can see here that my n_dim is 60. 60 features. So that is my n_dim. So it's the same as saying n_dim equals 60, but I've allowed Python to make that calculation for me, so I don't need to worry myself, using the x.shape 1, that's number of colon, and the n_class, I know that to be 2, R and M. So here I'm creating my model parameters, which is for my X, for my features, which is the capital X, and W is the weight, and B is the bias. So my X will be placeholder, tf.placeholder into tf.float32, comma, shape here, none, comma, n_dim. This n_dim is the shape, the colon of my capital X, which is 60 that we have here. So the none here means that it can take any number of rows when the epoch is running, but the colon cannot change, which is the 60 number of colons, 60 number of features, 60 features. So my weight would be a variable. If you look up my video on the AND gates, you understand why that is a variable, because my weight will change in the course of my epoch. So I need to put it in as a variable, tf.variable into tf.zeros, and I'm initializing it in this case with zeros. And the shape here, because my weight and my feature will multiply each other, then the row of my weight has to be equal to the colon of my feature. The colon of my feature is known, which is n_dim. So in that case, I'll just return n_dim as the row of my weight times the n_class. That would be the shape of my weight. And my bias in this case would also be a variable, tf.variable, tf.zeros in this case, and it should just be having a shape of 1 colon, which will be equal to the number of class that I have. So I'll just run that line. So I'm using this init to initialize all my variables. Init equals tf.global _variable _initializer to initialize all my variables. So here is where I'm trying to set up my cost function. So my y underscore, is my actual output in this case. So tf.placeholder into tf.float32, comma, the shape is what? None for the row, comma, n_class, which is the 2 classes of R and M. That's for my actual output. This Y here is my model output, which is coming from my from my perceptron. The model output is coming from my perceptron output, which is tf.nn.softmax. I have to run my matrix multiplication of the weight times features plus the bias. The matrix multiplication is affecting only the feature and weight. So, and I'm adding my bias to it. Then I will run it through the softmax addition function to get my model output. That's just the mathematical model of your perceptron. Let me just show you that again. The matrix multiplication of x and w plus bias, and that will run into the activation function. In this case, we are using the softmax because softmax will give you, let me go to that function itself. Your softmax will give you an activation function that will range from 0 to 1. 0 to 1. That's what your softmax will give you. And in this case, my one-hot encoder has already changed my output to 0 and 1. So I need an activation function that will also give me an output of 0 to 1. So that is why we are using the softmax in this case. Then my cost underscore function, so tf.reduce underscore mean. So what are we doing here? I'm trying to do the mean squared error for my actual y and my model output y, which is minus tf.reduce sum into x underscore times tf.log of y. This line, is making sure that my y underscore, which is the actual, right, multiplying it by the tf.log of my actual y, comma, reduce indices equals 1. If you recall when we are doing the MATLAB, the Excel for the softmax, here it is minus sum f5. F5 is the one-hot encode output, which is the actual output, times log of what? The log of the softmax equivalent of it. And from here, this y is already a softmax output because I'm getting the model output from the softmax instance. So what I'm doing here is the cross entropy. What I'm doing here for the cost function is the cross entropy on the softmax output of y. So that is why you have just what we did in Excel here. To get the cross entropy, it is minus sum into f5, which is the one-hot encode of that instance, times the log of the softmax instance. And that is what I'm doing here. The y is the softmax instance output, so minus tf.reduce sum into y underscore, this is the one-hot encode instance, times the tf.log of the softmax instance, and that is what I'm doing. Comma, reduction underscore, this is 1, is just the colon instance of it. So my train underscore step here equals tf.train. I'm using the gradient descent of the optimizer, and it's taking in the learning rate. So dot minimize the cost function. I want to minimize the error between the one-hot encode output and the softmax instance of it in the cross entropy. I want to minimize the cross entropy error. So that is what this line is doing, training my perceptron using the learning rate of 0.1, which I already put in, and I'm using it to minimize the cost function of the cross entropy. So that's what I'm doing here. So here is where I'm initializing my TensorFlow session. Sets equals tf.session, and sets.run. I'm running the init so that my variables can take in their initial values. So this is where I'm doing the epoch itself. So for epoch in range of training underscore epochs, I already specify training underscore epochs as 1000 here. The same way I did my learning rate at 0.1. So we're going to pick that value from there. So that'll be for epoch in range of 1000. So that'll be to 0 to 999. Sets.run. What am I running? I'm running the training underscore step, which is this. Training underscore step. I'm running this. I'll be running this, running 1, 2, 3. So training underscore step, the fit dictionary for that will be my X, which is the training instance of X dictionary, and the Y one-hot encode version of that, Y underscore, the training instance of the one-hot encode of Y underscore for the training underscore step, because my training underscore step requires two things: the learning rate and the cost underscore function. And the cost underscore function requires the Y underscore and the Y itself. The Y itself requires the X, the W, and the B. So that is why that is the fit dictionary in this case for my training underscore step. For the cost, sets.run cost underscore function. The fit dictionary in this case also is the X, the training of X, and the training of the one-hot encode version of the Y actual output. So my cost underscore history is to append whatever cost here to the empty list I created for my cost history. So to append that value one after the other to that empty list. That is the cost history that I'm doing here. Append the cost to this cost history that I created. So print, the print here is outside the for loop. So it's going to go into the printing the final value because outside the for loop. Print epoch as a string, the final epoch here. Then the cost also, it will be printing the final cost because this print is outside the for loop. So my period underscore y, we call session.run y, which is the model output, comma, feed dic in this case is the X test. So what I'm doing on this line is to now, the model that has been trained on 80% of the data, I'm now using it to predict what should be the output based on the X test that I have, that I have splitted initially. So that might take a while because it's 1000 epoch that is running, and this is the 1000 epoch. This is the final cost. Because I'm not printing this Y in this case, so that's why it's not showing up. So I want to do the accuracy here, and I want to use the correct underscore prediction as the identifier equals tf.equal into tf.argmax pred underscore y equals 1, comma tf.argmax test underscore y equals 1. So what this is doing here is to check the instances where my predicted y is 1 and the actual y test, which is the one-hot encode version of the actual output, is equal to 1. When both are 1, when they are equal, that is the correct prediction. So tf.equal, when these two instances are equal, that's what I want to know. Those are the correct prediction. When the model is saying it is 1 and the one-hot encode version also is saying it is 1, that is the correct prediction. So print mp.vstack, stack this thing vertically. Those instances, stack it vertically. So that will be print into mp.vstack into test.run. I'm running this correct underscore prediction. I'm running it in this session of TensorFlow because I've not closed my TensorFlow session. I opened it here and I've not closed it. So accuracy equals tf.reduce mean. I'm using the mean squared error. So reduce mean into tf.cast. This tf.cast, if you have seen my video on TensorFlow, you use your cast to convert tensors from one data type to the other. So if a certain tensor is a float and you want to work with it with another tensor that is an integer, you need to use the cast to convert one to the other. So in this case, my correct prediction in this instance would be in they will not be in float. They will be in a certain data type that will not be in float because they are 1 and 0, so they will be in integer. So I want to now use tf.cast on the correct underscore prediction to convert it into float, so that I can now do the reduce underscore mean on it, so that I can get the accuracy. So print this string test accuracy. Use these two single decimal place to format my sets.run accuracy multiplied by 100, and my percentage here is also a string. If I run this line, so these are the instances that the model is saying 1, and also the one of encode test 20% of y is equally 1. So those are the instances where they are true. When they are not equal, they will be false for the 20% testing. And here is the test accuracy, 83.33%, saying that the model is 83.33% accurate. So here, what I'm doing here is to plot my accuracy. So plt.plot, what am I plotting? I want to plot the accuracy based on the cost history. So I'm using the range here to know the range of my plots. So range equals length of my cost history, comma cost history itself. That will now be the my plot area. So my plt.axis. So I want to specify the range of my x and y axis. So 0 for the minimum value, and the maximum value will be the training epochs, which is 1000. So if you go to the x, as you can see, it's from 0 to 1000. So that's what I'm specifying here, 0, training underscore epoch. For the y, 0, mp.max. What is the maximum value of my course history for my y-axis? 0 to whatever the maximum value of my course history is. That is my y limit. So plt.x label, that is the label of my x. plt.y label, that's the label of my y. And plt.show test.close. This is now closing my session. So we can see from here that the cost began from about probably 0.7 or something and went down to here on the 1000th epoch, and that will be 0.4 something. So if I want to check, I can try to increase this number of epochs. Maybe the accuracy would be better in terms of, let's just go and make the epoch 2000, and let's see what's going to happen in this case. 2000, and let that initialize that there. Now let me run this line again and let's see. When my epoch is 2000, let's see if the accuracy will get better. So you can see now that it's further reduced the cost, which means if I increase my epoch, my model will train better. And we can see if I run this line again here, so you can see that my accuracy score went further down, So you can decide to increase the epoch so that you can get better accuracy. And That is, let me run this line and you see that. You can see, but my accuracy on the test is reducing. So you have to find a way to balance the number of epoch, the learning rate, and the accuracy score. So that's it on this session. Thank you very, very much.